Okay. So something a little bit asymmetrical, and I can remember, actually I can remember, it's nice to have lived things, but I mean, if you haven't noticed these kinds of signs, these protruding signs hang out from buildings, and I think somewhere in the homework or something, there's some trivia about this, about how at some point in the past 100 years, there had to be like bylaws in France about this, because people were, you can imagine like sticking your signs out, hanging off the side of your building so that people can see your shop as you walk down the street, and people were just making them bigger and bigger and bigger, and that was causing too much of certain forces, which we're about to discuss, to be applied to the building, to be required for tensile strength for the materials involved, compression strength for the materials involved, and these buildings had signs that were enormous, and some of them were falling off and hurting people, right? So they had to make bylaws about this. And so I read something, and I threw it in as a trivia piece somewhere else in the notes, about how they had to basically make it so you couldn't have signs off this on the streets of Paris. They had to be like mounted up against the wall, right? Like as a flat mounted sign. And I think we've seen that at convenience stores and things like that, but maybe in old timey downtowns. And I think about going to places in like Grand Bend or Niagara Falls or something like that. And sometimes you see these signs that are like sticking off the buildings. But if you go to a larger city like New York City, Toronto, whatever, oftentimes there will be bylaws about whether things are hanging off of the sides and they have to be like flat against the wall. And so I picture places like Subway or I don't know, some convenience store or something like that, where these lit signs are against the wall, so they don't have to deal with this kind of physics. But this is an issue. So I mean, in tourist areas, people like to be a little old-timey, and I've seen more of this. Okay, so let's like, you know, recognize that we don't see this everywhere, and even around the school we see some of these like kind of hanging out into the hallway. Sometimes they'll hang them from the track ceilings, which has its own problems because it pulls down on the track ceiling. But sometimes you'll see like these L bracket type things. Okay, so we got a 10 kilogram sign hanging off. Oh, is there a typo there? Off or a cable? Off of a cable. A cable. Oh my goodness. A cable and strut. I'm gonna have to go back and do some typo fixing. Support system such that the cable is angled at 40 degrees relative to the horizontal. So let's just throw that in there as a piece of information. Between here and here, it's 40 degrees. This is a strut, basically a support post, a cable, which could be a chain, it could be actual wire, it could be a metal piece. Anyway, such that the cable is at 40 degrees relative to the horizontal strut. Determine the tension in the cable and compression force exerted on the strut. So the cable's going to get stretched and the strut's going to get compressed. You can imagine this being kind of like a hinge kind of scenario, right? Reference frame. Always. Up, down, right, left, positive, negative, positive, negative. But in terms of the free body diagram, this is the sign itself. It would have a force due to gravity acting down on it. It would have, oh, wait a minute. What direction are the other two forces going to act? What direction would the cable act in? Is it going to be pulling up at an angle or pushing down on an angle? Yeah, up at an angle. It's going to go this way, in line with the cable. And what direction is the strut going to apply a force? Toward the wall or away from the wall? It's okay to point with your hand. Yeah? That way? It is, it's that way. It's away from the wall. In fact, there's two ways I know that. I know that if this thing is let go of, if I let go of it like a pendulum, wouldn't it swing towards the wall? And so something has to keep it from swinging towards the wall. It has to be a force pushing outwards. The other thing I know about, you know, pieces of wood or metal is that if I try to compress them, like a spring, they'll push back, right? We might not think of them like a spring, but everything compresses to a certain extent, right? So yeah, it's going to push back. So I'm going to call this one F2, just because the diagram to the left labels the strut number 2, and I'll call this one F1. Now, if I break this guy up into components, you know, whenever I draw a free body diagram, if I've already committed to these guys being solid lines, if I break something up into components, I'm going to do it as a dotted line so that the reader never thinks that there's this extra force there. I don't want to over-represent anything. This is about me being a good communicator. So I'll say this is F1x, dotted line. And we'll have F1y represented as a dotted line. Things that I've got in terms of my givens, based on the stuff that I just read, the mass of the sign is 10.0 kilograms. We're on Earth. Gravity is down. Theta 1, that's this angle right here, because there's only one angle this time, happens to be 40.0 degrees. So this is kind of like an asymmetrical pair of friends holding up a bag of feathers, like the problem we had before, only this time one friend is pulling up, the other friend is pushing sideways, which would be a weird thing to do for friends, right? It's a different situation, but it's not symmetrical, that's for sure. Again, though, I'm going to break things up, and I want to be X and Y. I want to be an X versus Y thinker. So this time, just like, for no particular reason, actually, I just want to start with the Y's, just to show that it doesn't matter if I start with X's or Y's. I think I started with X's last time. I'll start with Y's this time, okay? It's irrelevant what order I start in, as long as you're logical about it. But what I could say, as I'm setting up this equation, is, okay, it's going to be the sum of all the vectors involved. But, hey, gravity's down. I've called down negative. If I'm going to be somebody who inserts my negative signs when I build my formulas, I'd have to put gravity as a downward force now. If you're going to insert the negative signs when you bring in your variables, you can just say plus Fg, and you can bring the negative sign in with the 9.81. And that doesn't matter to me. That's a style choice, okay? Just be consistent about it. You can't do both. But the other thing that I think is, hey, if this sign is not falling or flying upwards, F net y has got to be equal to 0. So I can right away, in statics, make some simplifications if I know that I'm dealing with a static scenario. So 0 is equal to, and I could expand out F1y to be F1 times sine of theta. And again, if you want to wrestle through how I know it's sine of theta versus cos of theta, think that one out. You have to draw yourself a triangle. You have to think about, what am I trying to find here? That's my theta. I'm thinking about there being a force here, and I'm trying to think about that being the force that I'm talking about right now, the y component. So this would be the sine ratio, right? So, all right, minus mass times acceleration due to gravity. And actually, here I am like jumping to putting a 0 on the left-hand side again, and like thinking I'm going to simplify things. Things are already simple enough on the right-hand side. I want to start unloading things from the right-hand side. Take that negative MAG over to the other side, make it positive MAG, add it to both sides, cancel, cancel. And I get F1 sine theta 1. And what was I even trying to find here? I think I was trying to find F1, right? I'm trying to find how much tension there is in the cable. So we get MAG over sine theta 1 equals F1. And actually, as I look at that, I think Christmas came early. I know the mass, I know gravity, I know theta 1. I can actually calculate the tension. I don't even need the X information for this. That's great. I know this tension. I can like knock this one out in a second. Sub in my values. 10.0 kilograms. 9.81. Notice I'm not putting in the negative because I already dealt with the negative up here. Sine 40. And then somebody who's quick on the draw with the calculator. Arav, did you get it already? 152.616? Okay. Nice. Newtons. And if we wanted to be all roundy about this, it looks like we have 3 sig figs up there. So 153 newtons. And if we even wanted to add a direction to it, we could say it's 40.0 degrees above horizontal. Right? Because when we're looking at our picture, the cable is pulling up in this direction, 40 degrees above the horizontal. So if the goal was to find the tension, we got it. But the other goal is to find the compression force in the strut. And if a strut is not a word that you use very often, yeah, we're in the same club, because I don't use the word strut very often either, right? So if you're not somebody who builds houses or builds hanging signs or whatever, this might not be a thing that you talk about, but we should use proper language when we're talking about things. So I don't want to call it the compressy posty thing. I want to call it what it's called. It's called a strut. And so, if you're doing architectural stuff, you got to do some research and make sure you call things by the proper names. Anyway, I didn't even call that a net. I called it FET. F net Y. Anyway, F net X equals, now I could say F1X plus F2X, but where have I missed my negative sign? Yep. Yeah, it looks like that one's the one pulling to the left, which we defined as being negative. So again, if you're going to put in the negative sign, that's when you do it. Beautiful thing about statics is there's so many things that become zeros. Well, the nets anyways. So it makes it nice and easy, right? But I can say 0 is equal to negative, and I'll expand out the F1x to be F1 cos theta 1. And F2x, I don't actually have to simplify that at all. I can just call it F2. Because it's all x, right? There's no y component to it. I actually do want to make sure that I pause for this bit. I said once before that it's good when I'm doing these general approaches, or these specific approaches, to think about how I could be general later. And if I had a situation that was very much like this, I could come back to this. If I'd done all the thought process before, if this was going to be a recurring thing, I could say, hey, look, situations like this, that guy's going to be my equation 1. That guy's going to be my equation 2. But, not every two situations are the same. But if I did come back to this would be a good way to fast forward the thinking a little bit. Generalized equations people are always talking about. Anyway, if I wanted to get F2 all by itself, which I do, I'd take the negative stuff over to the left and I'd say positive F1 times cosine theta 1 equals F2. And actually, since we've already solved F1, we could just solve. Now, if I wanted to call this guy equation 1 primed, can you notice that if I hadn't done the whole left column, you see that I could sub equation 1 primed into equation 2, and I could treat this like a system of equations. And that's a nice mature thing to recognize, because we should be doing that like starting in grade 10. Of course we should do it in grade 11, and by grade 12 we should feel comfortable with recognizing if this is my equation 1 and this was my equation 2, or we can call them 1 primed and 2 primed, whatever, then we should be able to sub them together and solve by substitution, okay? So that's something that, again, as you're doing your homework, if the opportunity arises, try it out. Try solving by substitution, because what I'm doing right now is going through the process of subbing in these unrounded values. And every time you sub in unrounded values, you're going to increase the chances of messing up, right? Maybe you transcribe things wrong or whatever. You know what? Why don't we just do it? Why don't we solve by substitution this time rather than plugging in the 152.616? Let's just solve by substitution. Was that theatrical enough? Like I acted out my whole thought process? Let's do that, okay? Sub in. So we would say F2 is equal to MAG over sine theta 1 times cos theta 1. Now there's going to be somebody who gets really excited about this. And they'll be like, what? Sine theta in the denominator, cosine theta in the numerator? Isn't this just 1 over tan? Who else is excited? I'm excited. Love it when I can make use of even the simplest of trig identities. Isn't that good? That's so cute. That's such a cute little formula. Anyway, we sub in our values, 10.0 kilograms times 9.81 meters per second squared. We already dealt with all the negatives, none of that. And then tan of, what was it even, 40 degrees? And I know that I kind of painted myself into a corner here. But what does it end up being? Unrounded. Does anybody get a 6, a 1, and a 1, but not in that order? 116. Can I just stop at 910 then? Yeah. Okay. 116. Wait, what's that? Yeah? Sorry, what was it? 911. I'll stop there. All right. Newtons. And if I was going to round it off to 3 sig figs, of course it's going to go to 117. 117 approximately newtons. And since it's force 2, we could just say that it's to the right. And I definitely did work myself into a corner. I don't have enough space for my therefore statements, but out loud and in words, I got 117 newtons and 153 newtons. Now this guy here is a compression force, compressing the strut. This one's a tension force, and people could talk about like how strong the materials are. And actually, you know, from a realistic point of view, this is something we'd have to deal with for engineering design. Can you guys please take a look at this question? I'm going to read it out loud, but look at this question. Let's see, for engineering design, how could we deal with this? It says, for the structure above, the cable supporting the sign has 500 Newton tensile strength. Now, tensile strength is the amount of force that something can withstand before it snaps due to trying to pull on it, like a cable or a string or fishing line or something like that. Tensile strength is a measure of how much tension a material can withstand before structural failure occurs. A foolish 70-kilogram teen jumps up and hangs off of the sign. This effectively makes the sign into an 80-kilogram object. Now, I watched this at Grand Bend on an old-timey street, and I don't want to perpetrate any negative stereotypes or whatever, but it was a boy. And you never see anyone other than a teenage boy decide, I'm going to hang off of a sign that some business owner has put up. And I know that they assume in their brain that that's going to impress somebody, because of course they can reach this sign, which was hung at arm's length. But anyway, the thing is, we have to engineer around humans. So this is something that somebody might have to think about, is engineering around this human. Other things that you might want to think about engineering around, because we want to over-engineer things, people say, is ice accumulation. You can imagine, even in the absence of idiots, ice will accumulate sometimes, because I don't know if you know Grand Bend, but it's right by Lake Ontario, and so there's always going to be ice accumulating on these signs, unless they're going to take them down in the winter, which I suppose they could, right? Tourism being at a low season. But anyway, let's see if we can figure this out. Will the cable snap? Before we do this, how would we approach it? What would we need to do? Could we use the equations up above? Which equations would we use? We have a few that we've actually given names to. I could even, if I wanted to, I can call this one equation 3 if you like. I've got equation 1, 2, 1 primed, and 3. Which ones would help me to figure out if this cable's going to snap? Because I feel like I'm generalized enough, I could just sub in some numbers. What do you like? Yeah?
1 prime.
Yeah, look at this. Wouldn't 1 prime going to just give us the force value? Can you guys do it? Take a minute. If somebody's watching on the video, pause it or whatever. But can the people in the class, could you just calculate what F1 primed is for the new mass? The new mass is 80 kilograms, okay? I don't have this one calculated, so I can't just say this is the answer, okay? So sub in your 80 kilograms into 1 prime. And what we're trying to figure out is what's that force that would result as tension in the line, in the cable, and does it exceed 500 newtons? Now the thing about this is it's not just good for hanging signs. There's a nice little out jut, like lookout at Niagara Falls, where people would have to think about this kind of thing. Anything cantilever, you would have to think about this kind of thing. diving boards, for goodness sake, I suppose you'd have to think about. Like, I don't know, there's all kinds of situations. All right, what do you end up getting? Yes, sir.
1,220.19.
What was it? 1,220? Wow. Is this sign falling down? Yes, it is. So, I mean, if you ever look at these signs that are being held up and you're like, oh my gosh, that's quite the chain that's being used as the cable in this scenario. Or, oh wow, look at the girth of that cable, as one does when they walk down the street. That's why. Because we got to defend ourselves against the idiots or the ice, right? Like, we really do. It could also be that people make it like super strong because in the future they want to think about what other ridiculous signs they could hang off of the first one. Sale! Going out of business! I don't know, whatever it is you plan for the future, right? Like this is some, sorry, that's dark, but we all got to think about what's next.